Right, hello everyone. Welcome to this week's Astronomy Talk. I'm Xavier, the chairperson of the society. Tonight, we are very honored to have Professor Chris Lintott with us today to give a talk titled The Surprising Universe. Before we begin, here's a short introduction about the speaker. Professor Chris Lintott is an astronomer who specializes in galaxy formation, machine learning, including anomaly detection, and occasional planet hunting. These projects usually make use of the Zooniverse citizen science platform, working in collaboration with more than 2 million volunteers around the world. He is a member of the collaboration building the Vera Rubin Observatory, which will power the next astronomical revolution. He is also an author, a broadcaster for the BBC's long-running Sky at Night program, and involved in all sorts of public engagement and outreach programs. His recent work attempts to understand the properties of interstellar objects passing through the solar system using cosmological models of galactic evolution and chemical models of planetesimal formations to understand how the properties of objects like Oumuamua depend on their origins and what these objects can tell us about the processes on many scales. He's the lead editor responsible for laboratory astrophysics, instrumentations, software, and data for the Journal of the American Astronomical Society, including the Astrophysical Journal and the Astronomical Journal. He also runs the research note on AAS, which encourages short, moderate report on works in progress, observational notes, and importantly, negative results. He's a fellow at New College, University of Oxford, where he helped lead the Bowson Center for Cosmological Studies. In the department, he chairs the Access and Public Engagement Committee and is one of the team of harassment advisors. He is also an elected member of the board of directors of the Ashmolean Museum. Now, without further ado, Professor Chris Lintott, please.
Thank you. Does anyone mind if I take my mask off? I'm happy to lecture with it, but I will hear myself and you'll hear me much better without it. So thank you. And thank you for being here. I know what is it, week 6 in Cambridge? I always have to translate from Oxford to Cambridge these days, but I know week 6 this term is busy. So thank you for coming out and being here, and hello to everyone online as well. Please do interrupt. I know I will try and leave plenty of time for questions at the end, but I'd much rather you interrupted me as we go. I will try and keep an eye online to see if you interrupt as well. Just type in the chat if you have a question. It's always a delight to come and talk to QAS, having spent many years sitting in the QAS audience. So I'm excited to present to you what won't be a very good talk. I seem to always come here when I have new thoughts and new ideas, and I'm going to try and sort them out by talking to you. And really, what I'm struggling with at the minute is trying to think about how we do astronomy, how we professionals, but how everyone interested, does astronomy in a world where telescopes have got large, data sets have got big, and computing has got powerful. Those things have driven the way that astronomy has changed and evolved since I was here 20 years or so ago, and trends are accelerating in those directions. So I think that's a good thing. We've made, as I'll try and make clear, all sorts of discoveries because of big telescopes, big data, and clever computers. But it's also changing what it means to be an astronomer. It's changing the skills that some of you are learning if you're going to go on and do astronomy. Software development has always been important, but it's really important now. Statistics and machine learning and all the things that go with it are vital research skills, whereas it wasn't that long ago where there were things that some people were kind of interested in because they were fun. But they're also meaning that astronomy is becoming, to some extent, a science of experiment, which we've never really been before. Traditionally, I think of an astronomer, I don't know what you envisage, but you think of somebody at a telescope, making observations, looking at something, taking an image, taking a spectrum, maybe taking a deep image like the Hubble Deep Field or something like that, and trying to work out what they see there. In other words, using an observatory in the same way, actually, that people would have used the Northumberland or whatever else As opposed to writing proposals to say, okay, give me $1 billion, I will build a telescope, I will measure the space of 10 million galaxies, I will plug them into a formula, and I will test whether the universe is continuing to accelerate in its expansion, or whether it's slowing down, or whether it's constant. Now, that's a perfectly valid way of doing science, but to me, it's not as much fun as pointing the telescope at weird things. And so the question I want to first convince you that there's good science to be done by being surprised by unusual things in the universe, by doing this old-fashioned thing of pointing telescopes randomly, not quite so randomly, at interesting stuff. And then I'm going to talk a bit about how we might still do that in this world in which computers are clever and data is big. So let's start by convincing you that being surprised can be important in science. And there are thousands of examples I can give. I think my favorite, clearest example of somebody being surprised productively by the data comes from this place. This is, of course, Saturn's moon Enceladus, which is an icy moon. It's about the size of the UK across. And this is an image of its south pole where, as many of you will know, there are fountains of water extending out into space. Now, before the Cassini probe visited the Saturn system, no one knew that this happened. Enceladus was another boring icy moon, a dot in the telescope, a distant blob in some of the Voyager images, and essentially just thought to be an inert lump of ice. There was no reason to believe that something this small could be active. Cassini happened to fly past it on one of its first loops around the Saturnian system, and most of the instruments on board the spacecraft were off. But the magnetometer, the long boom on the spacecraft that records magnetic fields, that's primarily designed to think about the interaction of Saturn's magnetic field with the solar wind, particles streaming from the sun, was on. And Michelle Doherty and her team at Imperial College and elsewhere noticed that as they'd flown past Enceladus, there was this blip in the data. They detected a disturbance in the magnetic field. There's no reason to expect one. They weren't looking for one. They hadn't written a proposal that said they would look. It's just that their instrument was on as it flew past Enceladus. Michelle is one of the scientists I admire more than anyone else because she allowed herself to get distracted. Her and her team got very distracted by what could have caused the signal that they'd seen in their data. Actually, incidentally, they later found a similar signal in Voyager data. So if people had got distracted 20 years earlier, we might have known about Enceladus fountains more recently. Anyway, the upshot was because Michelle and her team got distracted and interested, they persuaded the Cassini team, next time there was a flyby near Enceladus, to turn on their cameras and to fly much closer to the South Pole than the spacecraft had been planning to do so. In fact, as it turns out, they flew much closer to the spacecraft than we'd now consider safe, because they flew through these fountains and had their cameras on, and we discovered that Enceladus has an ocean within it, and that ocean is active and spraying out into space. And actually, this material seems to form one of the outermost of Saturn's rings. I think it's the E ring, comes from Enceladus. So this is suddenly a place that has an ocean. We know from measurements in situ made by Cassini that the water is salty. And what that tells you is that that ocean has a sea floor. So there's a place where the water comes into contact with rock. And so this becomes one of the most convincing possible habitats for life anywhere in the solar system. But if you look at a book written just before Cassini got there in the late 90s, then no mention of this is made. So we had no idea. We didn't even know to go and look at this. So it's a proper story of scientific discovery. But the thing I want you to remember was that it happened because the scientists got distracted and was able to follow up on the weird thing that they'd seen in their data. Of course, there are older examples as well. I can't possibly tell this story here without mentioning Jocelyn Bell Burnell. I know she talked to QAS a few weeks ago, so I won't labour the point. But out at Lord's Bridge, of course, Jocelyn was making measurements of the Milky Way and trying to study the radio sky for the first time using this magnificent, slightly odd device made of chicken wire. If you haven't been out and seen it, it's there, it's rotting away in the field, but I think it's quite special to go and stand next to it. And you probably know the story that they discovered what Jocelyn described as scruff on the data. So this is an old-fashioned printout of data from the radio telescope. The red line is the signal. Time goes left to right along here. And just here, there's this little bit of scruff, this little bit where the recorder has shivered a bit and recorded something there. Normally that's interference, but there was this source seen every so often that repeats. And again, it's about letting yourself be distracted. Jocelyn's role wasn't to discover pulsing sources in the sky. She was trying to do something else entirely. And I love the fact that when she tells this story, as perhaps she told you, she remembers cycling back into Cambridge from Lord's Bridge at about 2 in the morning, being annoyed that this discovery was going to delay her PhD, that it was going to get in the way of what she was supposed to be doing. There was also a period, as you probably know, where the signal was jokingly known as LGM1, for Little Green Men 1, because a regular signal was the kind of thing that you might expect to be an artificial signal. Now, I don't think Jocelyn or Anthony Hewish really ever believed that this was an alien signal, but they gave it the name, and Jocelyn remembers being annoyed that it was aliens that were going to describe her PhD, not excited by the discovery, but annoyed that this was getting in her way, and yet she still spent time to try and work out the source of the signal. It quickly became apparent that there were several of these things, and these are these dense, compact objects that we now know as pulsars. And there have been more than 50 years of research and dedicated telescopes and time built to try and understand these things that came from an astronomer being distracted. Radio astronomy actually seems like quite fertile ground for finding the unexpected. I guess we've had a longer history in the optical of taking images, and although we can be surprised, as I'll show later, I think radio astronomy has a particular legacy of this. One of my favorite stories comes from this place. This is Parkes in Australia. This is the dish, if you've seen the film. This is the telescope that had a sideline in being the southern link of the communications downlink for the Apollo missions, but it's normally a radio astronomy facility. And a few years ago, they got very excited by finding bursts of radio waves that seemed to be coming from various bits of the sky that were fast, that were all at the same sort of frequency, but seemed to be detected from across a wide band of the sky. Nothing like these things had ever been seen before. They gave them the name peritons, and they published several papers and asked other radio astronomers to look at these sources to try and find them or to find similar signals. What was odd, though, was that no one else could see these peritons. No other observatory could detect, even in the same parts of the sky, and even at the same wavelengths, no one else could detect these bursts of radio waves that were being seen by Parkes. And that raises a few alarm bells, I guess. But Parkes is a top-notch observatory. Its engineers build wonderful receivers that are highly sensitive. And so for a while, the idea was that they were just better at this than everyone else. Eventually, they put out a paper that catalogued the first few years of observations of these peritons. And it had 2 telltale figures in it that contained the solution to the mystery. Here's one of them. This is the local time of the peritons by detection. So you can see, and this should have been a red flag really, that whatever celestial object is causing these things, it knows when lunchtime at the observatory is, right? They tend to occur in the early afternoon. The other figure showed a frequency diagram of these things and was seen by a retired engineer who used to work on microwave ovens, who immediately recognized the signal as what happens if your microwave is faulty, such that if you open the door before the timer stops, normally a microwave will cut off instantly. That breaks, you get a burst of radio waves that has a particular signature, and that's what they've been detecting. The microwave in the visitors center was broken. If you ran it, if you put 2 minutes and you let it run, no problem. If you put 2 minutes on, got impatient and opened it, you would create a periton. And so they'd managed over the course of many years to systematically study their own microwave. Now, this sounds like failure, right? And I think there was something, but I think they're just about finding it funny now. I particularly like that there's a side story, which is that Tim O'Brien at Jodrell Bank had a summer student and a pile of microwaves, and they spent the whole summer trying to break a microwave in just the right way to produce these things. And it took the whole summer, but they eventually got there. So, you know, it's quite a subtle thing. But actually, I think the story of the peritons is pretty much perfect for astronomers who want to investigate the unusual. They found a phenomenon. They looked at where it was on the sky. They looked at its properties. They came to a conclusion about what it was. All right, it didn't turn out to be a pulsar or a new exciting form of transient. But at least they published their data. They did everything in the open, and eventually the mystery was solved. The people who've suffered most, perhaps, are a different group of researchers who, at the same time, were finding real radio transients. So this is what's called a waterfall plot. So this is the output from a broadband radio telescope. So on the y-axis here, you've got frequency from low to high. Sorry, other way around, from low to high. And then this is just time along the x-axis. So time flows from left to right on this diagram. And the color tells you the intensity of the signal being received by the telescope. So bright pixels tell you that there's a signal there. So you can see that mostly this is noise. So dark pixels in this tell you there's a signal there. So most of this is noise, and then there's this signal that stretches. It's a chirp, actually, so it changes frequency over time, but this is a very distinctive signal in the data. And these things have been seen frequently. They're called fast radio bursts. This one is called the Lorimer burst, which was found in archived data by a summer student and a researcher who were looking for unusual signals. And they found one of these things, again at Parkes. And then this time, other telescopes have found these fast radio bursts. They're described by essentially how they sound. They occur at many different wavelengths. They occur across the sky, which turns out to be important. And they last only a few seconds at most. But they appear to be very powerful radio signals. And so you have to play this game again of identifying a phenomenon, seeing what we can find out about it. So far, we don't know much about fast radio bursts. We've learnt that they come from all over the sky. And that tells you something immediately. It tells you that they're either very close or very far away. And the reason I can make that assertion is because of just geometry, right? If things are associated with the solar system, well, almost everything in the solar system is in a plane. So all the planets are roughly in a plane all the way out to the Kuiper Belt and Pluto. So if this was a solar system phenomenon, we'd see it following the zodiac on the sky. Maybe it's to do with the Oort cloud of comets out there, but that's a bit exotic. If it's to do with the Milky Way, well, the Milky Way is a disk. Our galaxy is a disk. So if these things live in the Milky Way, then they turn out to be, they should follow the Milky Way on the sky. They don't, they come from all over the place. So they must be very distant, or they're to do with low Earth orbit. The fact that they change frequency turns out to be a phenomenon called dispersion. It's to do with the scattering of radio waves as they travel through space. And so that also gives you a clue that these are distant objects. So we think these fast radio bursts come from distant galaxies. The second thing we've worked out is that at least a few of them repeat. In other words, we've seen the same bursts, same type of bursts from the same galaxy. That's confusing because these are powerful objects. You normally in astronomy think that if something explodes, something is bright and luminous, you normally think that it must be something exploding. But something repeating means that it's not a fatal explosion. So we need to come up with an explanation for these things that involves something having a powerful eruption that isn't fatal, but not all of them repeat. So it's possible there's two kinds of phenomena going on here. There might be a type 1 and a type 2 radio burst that we don't understand yet. A few of them have been tied down to particular galaxies. There doesn't appear to be anything unusual about the galaxies that we find them in. Sometimes the same galaxy will produce bursts at different frequencies. That's pretty much all we know about these things. What's happened is that there's a telescope in Canada called CHIME, which was built to do cosmology. It's supposed to do something else. In fact, it was built to be the kind of experiment that I talked about modern astronomers relying on. Actually, it turns out it's brilliant at finding fast radio bursts. There's a bunch of very distracted astronomers who thought they were going to measure the cosmological constants of the universe. And actually, they're busy chasing exploding things in distant galaxies and having a whale of a time doing it. What we're doing about radio astronomy, I just to be topical, there's another new kind of burst found by Natasha Hurley-Walker and a team down in Western Australia using an instrument called the MWA out in the far outback, in literally the middle of nowhere. So they found a strange phenomenon called Gleam XJ 1625759.5 minus 523504.3. Really needs a name. Really needs a name. Anyway, this Gleam X source, Gleam X is the survey. These are bursts from it over the course of a few months. And it repeated every 18.18 minutes, which is not a time scale that other things in the universe seem. We used to think pulsars are seconds or milliseconds. Variable stars are days and weeks. Anything involving orbits is days and weeks. So we've got something varying on an 18-minute time scale. Again, we think it's distant. And this is the sort of brightness over time for subsequent peaks. You can see it looks different each time. Sometimes it has this double peak. Sometimes it has a slightly more complex structure. Sometimes it's just a straight up and straight down. So we don't know what this is at all. We don't think it's aliens because it's very broadband. It's across many frequencies. And the idea is that if you were an alien race communicating, you wouldn't be wasteful. So why would you send a broadband signal? But we can compare it to other weird things. So this is the landscape of radio transits, of anything that varies in the radio. So on the y-axis here is the luminosity. And then radio astronomers are strange people. So on the x-axis here, this is sort of the time scale on which things vary, multiplied by the frequency of radio wave that they emit, which is just a useful way of sort of compressing three sets of data onto a two-dimensional graph. But it's actually quite a useful way of separating out things. So right at the top here, these are the fast radio bursts that I was talking about. So these are our recent discoveries that we don't understand. They're very bright, and they vary, they last only a few milliseconds. Down here in blue are Jocelyn's pulsars. These vary on second timescales. They're much less bright with almost all of them that we know of are in our galaxy. So they're less luminous. There's this strange category of an R-rat. These are, you could think of as weird pulsars. I don't have time to talk about them today. And then over here, you have things that go bang. So we've got supernovae, X-ray binaries. Right at the top here, we've got gamma ray bursts and exotic explosions. And our Gleam XJ, whatever it is, each of the bursts lies about here. There's one weird burst. So it's not quite a pulsar. It's not a fast radio burst, but nor is it a supernova. So just by looking at this diagram, all we can really conclude is that it's weird, right? And so when you find weird things, you have to ask, how weird is it? Well, these are in different places from everything else. So either we've missed a whole population of things here. Maybe there are some faint pulsars or something that we haven't found yet, or slow pulsars, maybe. Maybe 18 minutes is one thing. These are all seconds. Maybe we're missing pulsars on minute scales. That's unlikely, but it's possible. Or this is a whole new category of thing that we haven't understood yet. And given that they only announced it a month ago, I don't have an answer. So I know I've just thrown a load of radio astronomy at you, but really the point I'm trying to make is that this kind of thinking is interesting. I found a weird thing, how do I compare it to other things? But also that we're still discovering things. I think it's really easy to give a talk like this or to write a textbook or something And you have your nice category of radio transients. Let's list all the things that we know of. We've got pulsars, we've got gamma ray bursts, we've got all the rest of it. But actually, this is a mess. We don't know what's out there yet because we're still building newly sensitive instruments and exploring bits of this diagram and many other diagrams. And that's true every time you look at it, at the universe in a new way. We find new things. Another really good recent example of that comes from another phenomenon. I am, by the way, missing my lecture notes, so I'm going to forget names of things. This is, I think, if anyone can correct me, I'll be impressed. I think this is NGC 4993. Anyone going to call me on it? It's not labeled, is it? No. This is a relatively nearby galaxy that in 2017 had this transient, this bright star that appeared and disappeared. Googling is cheating, by the way. No, I'd appreciate it. Bright star that appeared and disappeared. It was also detected in gamma ray bursts, but it's a famous one because it was also detected in gravitational waves. So this is the only object so far that we've seen both in electromagnetic radiation and also in gravitational waves. So this is supposed to herald the dawn of multi-messenger astronomy, where we can observe the universe observe the same phenomena in different ways. I should note, for those keeping track, that we've been doing that for a while. If you care about particles, supernova 1987A, for example, was detected in neutrinos as well as optical light. But the gravitational waves are special, so let's just talk about them for a sec. So this is Virgo, I think, which is the European contribution to a network of gravitational wave detectors. So we're looking for ripples in space. Many of you may know how this works. It's, at principle, a really simple experiment. What you do is you have an optics lab here. In the optics lab, you take a laser beam, you split it into two, and you send it off down two vacuum tubes, which are precisely at right angles. And the longer these arms are, the better. Virgo is just outside Pisa, and the arms are 2 kilometers long. They're 2 kilometers long because there's a motorway down here and Pisa Airport just here. So you have to constrain your physics based on the land that you're given. Why you build one of these things in a vaguely geological active place just outside a city, I'm not sure, but that's what the Italians had money to do. Anyway, 2 kilometers down the track, you hit a mirror and the laser comes back. And if all is normal, then because these beam lines are exactly the same length, the light goes out and it comes back and the two laser beams arrive at exactly the same time. You can check that by having them interfere with each other when they return. If something happens while they're traveling, if a gravitational wave, a stretch in space, travels through the instrument while the light beams are on their way, then one may take longer than the other because this beamline may be stretched. And that difference, which is tiny, over the course of a couple of kilometers, the change induced by a gravitational wave might be something like the size of an atomic nucleus. But if you can combine the two lasers with that sort of precision, you can detect this stretch and understand that space has stretched, that a gravitational wave has passed through. It's an insanely complicated experiment. Well, it's very simple. It's very difficult to do because of the precision required. For 40 years or so, people plugged away with building this kind of experiment, trying to get more and more sensitive, knowing with many of the generations of experiments that they built that they wouldn't discover anything. Because we'd predicted how strong gravitational waves might be. And so it wasn't until about 2015, I think, that the first signals were found. There's an awful lot of background noise. Obviously, things like passing trucks will cause vibrations, but so will seismic activity, so will even the passage of clouds across the top of the observatory may have a significant gravitational effect at times. And so the best way to make sure that you really are detecting real signals in your gravitational wave observatory is to have multiple observatories. So we have Virgo in Europe, but there are 2 LIGO observatories in the States, one in Washington State and one in Louisiana, I believe, but down south. And they can detect these signatures. So here is the first real signal that they detected. Hopefully you can hear this with the mic. We're going to have to just broadcast. So that's normal and then sped up. So you can hear that chirp there. So that chirp that goes from low to high, as pictured here, is because the waves are getting closer together. And it turns out that that distinctive signature is the signature of two black holes colliding together. So they spiral inwards and they get closer and closer and closer. And so the gravitational waves that they give out get closer and closer together. So we can detect now, without having to see them, the merger of black holes out in the universe. It's the opposite of a surprise, really. I'm supposed to be talking about the surprising universe, but there was 40 years of effort to detect this signal. But what's been interesting is that these are much more plentiful than people expected. And we've been able to categorize the black holes that have been seen. So based on the chirp itself, you can work out the properties of the two black holes that are merging, and you can work out the properties of the black hole that they produce when they've merged. So this is sort of a family tree of black holes that we have detected. So we can see here, and it's not brilliant on the screen, but there's a bunch of purple points down here. These are stellar mass black holes that we knew about before. So we know about them because they've been detected in orbit around other stars, or they form things like X-ray binaries where they interact with the star. Down here we have neutron stars, which are obviously smaller, which we know about because, again, we see them interacting. And we've seen the occasional black hole neutron star merger. So this black hole is merged with this neutron star to form a black hole that's here. So we're beginning to see this sort of thing. We've also at the top here got lots and lots of black hole mergers that are producing these very massive black holes. And so the surprise here was that these massive black holes, of maybe 100 times the mass of the sun, are pretty common. We've seen lots of events that produce them. And even though LIGO is sensitive to a large volume of the universe, we weren't expecting to see so many signals. So the team actually detected more collisions than they thought they would. In fact, that first detection came when they just turned their machine on for the first time. It came during commissioning, and they assumed that it was a test. So when you play this sort of thing, detecting the signal is really difficult. And so the teams have a policy of blinding the results. So there's a few people in these large collaborations who can inject fake signals into the data. And they do so quietly, and they don't say anything until it's gone through all the system, and people have found it and argued about it and discussed it. And at the point where they decide to publish a paper on it, then somebody puts their hand up and said, actually, no, that's one of our fake ones. And so everyone involved in this LIGO discovery, when they saw on the first day of testing, they see a signal, everyone, I think, believed it was fake. Turned out to be real. And there's this moment where they said, okay, we're going to publish this paper, and the people who are responsible for faking them went, no, that's not one of ours. And they realized that that's the moment where most of the team realized they'd discovered something. But there's something else interesting about this, which is that everyone got involved. I told the story slightly backwards. So we found the first one, and then there was this thing 2 years later where we had a gravitational wave. We also had this optical transient. So for the first time, we could connect the two things. We could say, okay, we know this is a merger of two compact sources, because we see the gravitational waves. In fact, it's two neutron stars merging. But also, we could see the effects. And there was some brilliant science that came out of this. And my two favorite results are confirmation that about half of the gold in the universe is made in collisions between neutron stars, because we could see that from the spectrum of this. If you're wearing any gold or you see any gold jewelry, half of that comes from explosive events involving the collision of neutron stars. The other one is very simple, but the gravitational waves arrived at the same time as the light from the collision. And so this is proof that gravity travels at the speed of light, which is a fundamental prediction of relativity, but not something we've been able to test to this accuracy. And it's a really simple observation. Two things happened at once over the course of 140 million light years. And so that's a decent test. to unprecedented accuracy of that particular prediction of relativity. But to make all these observations, something like 1,200 astronomers were involved in following up this explosion, because once they realized they had this detection and it coincided with the gravitational wave, people started calling everyone they knew to get telescope time. Basically, every telescope on the planet was involved in following up on this object. It must be certainly the most studied object of the last 25 years. And so what that meant was that this was the worst kept secret in astronomy. The paper describing the results came into the journal that I'm an editor of. I wasn't the editor, but I know the people who were. And trying to find anyone who could referee this paper was a nightmare, because absolutely anyone involved in observational astronomy already knew about it and had taken part in the follow-up. So what this tells us is that this game of finding unusual things has to be collaborative. If I find something unusual, I need your telescope to help me follow it up. This isn't the world of don't look up, where you find something unusual, keep it quiet, or tell the government and not your fellow astronomers. The first thing you do is tell other astronomers. So one of the reasons I like working in this way is that it forces us to collaborate with each other and to collaborate around the globe as well. This becomes a feature of what I'm going to say, I think. But despite that collaborative nature, there's also a selfishness here. One of the reasons I want to play the game of finding unusual things is that I like the idea of having things named after me. I always have done. I've always wanted to make a discovery. I particularly, certainly when I was growing up, wanted to try and discover a comet. Not just because comets are intrinsically interesting, which they are, he said, looking at the senior treasurer in the corner, but because comets are named after their discoverers. If you find an asteroid, you have to name it after somebody else, which is, fun, but not that much fun. If you find a comet, it's named after you. And so I was quite hopeful that Comet Lintott, I think Comet Lintott's got a ring to it, if I'm honest. I've yet to find a comet. I haven't put a huge amount of effort in. But I did try for a while with a little 6-inch telescope that I had at home to just keep an eye out, just in case I could find something. The days of comets being discovered by 14-year-olds with small telescopes are long gone. I did make one discovery of this thing. This is my favorite object in the night sky, is the Orion Nebula. If you've seen it through the Northumberland, you know it's a wonderful sight. But even through a small telescope, it's one of the few deep sky objects that actually looks like it's supposed to, even through a small telescope. You have to get your eye in and maybe use a bit of imagination, but you could see the gas, and you could see how it curls around the young stars that are forming in this nearby stellar nursery. And I must have spent hundreds of hours of my life looking through telescopes, looking at the Orion Nebula, just enjoying the view and trying to get my eye in and see all the fine detail. I was doing that one evening when I was indeed about 14 and nudged the telescope and found this thing. This is a cluster that lies just to the north of the Orion Nebula. And it fitted perfectly in my telescopic field of view. And I remember thinking, I didn't know there was a cluster here. It's surely a very striking and beautiful sight. Surely somebody must have found this. And this story is getting increasingly hard to explain because we didn't have the internet at home at the time, but I had books, which you'll remember from, the past. I had an atlas of the sky, and this cluster for some reason was not on the atlas. And so I called it Lintott 1. And I remember very carefully plotting it. And when I got to school the next day, I discovered it's actually NGC 1981. It was discovered, well, it's been known for a long while, I'm sure, but Herschel catalogued it in the 18th century. And, it's a very well-known object, and astrophotographers rather like it because it's very beautiful next to the nebula. But for a night, I thought I'd found something. And that was as close as I thought I was going to get, because as I came to Cambridge and studied astronomy and went and did my PhD, as I said, I've spotted the shift to experimental astronomy. And I think that the telescope that really embodies that is this thing. This is the telescope used by the Sloan Digital Sky Survey in New Mexico, on a site that has, a bit like Cambridge, has 320 clear nights a year. And for the first 8 years of its existence, Sloan did this remarkable thing. It just made a map of the whole sky. So on most nights, it just let the sky turn above the telescope, and it took pictures in 5 different colors. So that it could build up a color map of the sky. And then on the clearest nights, it took, it went back to the million or so objects in the survey, which seemed to be galaxies, seemed to be faint, fuzzy objects. And it measured the distance to them. And so what you got was a 3-dimensional map of the sky. And so we could sort of fly through that. This is about half the data. I need to update this really. So this is about 500,000 galaxies. And it was really surveys like Sloan that told us there's something remarkable about the universe. Not just that it's pretty empty, so each dot here is a galaxy, but when you get out to about this far from the Milky Way, you start to see that there's structure here, that there are places where there are loads of galaxies and places where there are very few galaxies, that we have these giant filaments and galaxy clusters and superclusters, and then these relatively empty voids between them. And so we'll stop in a second and rotate, and you get a sense of the sort of the honeycomb nature of our universe. And studying this large-scale structure has been one of the big breakthroughs of the last 20 years since the first Sloan release in 2005, because we've learned that the properties of a galaxy depend on where it lives. So whether you're in the middle of a supercluster or in the middle of a void really matters. Lots of the material that fuels star formation in galaxies flows down to the large-scale filaments. There we go. Ignore the fact it looks like a bow tie. We just haven't filled in the gap in the middle just yet. But you can see what I mean about the honeycomb structure. And we've also worked out that you can use this honeycomb structure and the scale of the voids and the size of the filaments to constrain cosmology. So you can work out the history of the universe by comparing the structures that you see in this large-scale structure to the cosmic microwave background. But you do that by treating each galaxy as a point, as a test particle, and not really looking at the images. It's sort of what you get when you get cosmologists and particle physicists to build you a telescope. It moves systematically, it creates this data set that you reduce to one number, which you announce to the world. Except that, because of a remarkable man called Jim Gunn, who's a cosmologist and instrument builder and sort of all-round genius, Jim realized that it didn't cost that much more to have the telescope take images of these galaxies as well as just record their position. And that meant that we could understand a lot about the galaxies just by looking, but it also meant that we could use this survey to try and find unusual things. And it's something that I got involved in when, in 2007, we launched a project I've talked about to QRAS many times, which is this Galaxy Zoo project that invited the public to go online. You can still do this today, to come online and classify galaxies by shape. Something that's important if you want to try and understand galaxies. If you want to hear those stories again, you have to invite me back, and I'll talk about QRAS. So mostly we were trying to do things like distinguish spiral galaxies from elliptical galaxies. So these two galaxies are different shapes. They've had different histories. The shape of a galaxy tells you about how it's interacted with its surroundings over the last, 10 billion years of cosmic history. But it turns out that if you actually just look at all of the galaxies, and because we had hundreds of thousands of people looking at the million or so images of galaxies that we have, people get distracted and they start to find the unusual things. And something that happened very early was the discovery of this thing by a Dutch school teacher called Hanny van Arkel. And this is, the green blob there is Hanny's voorwerp, which turns out to be Dutch for thingy. We thought it was a technical term, so this is now what this thing is called in the papers and in the literature. But this was a wonderful cosmic mystery. So, is this the original image? This might have been the original image that we had of the voorwerp. And Honey just did the very scientific thing that we've established of getting distracted and wondering what the unusual thing is. You know, why is there a sort of misshapen Kermit the Frog or a suffering Romulan battle cruiser or whatever you see in this blob sitting next to my nice galaxy? We didn't know. Our original idea was that this thing was probably a planetary nebula, a feature in our galaxy that just by line of sight happened to be in front of this other galaxy. So we took advantage of a black market in telescope time that sort of doesn't exist anymore. But I had a friend who was observing in the Canary Islands, so I called him up, gave him the coordinates of this object, and by complete coincidence, the first thing you do when you start an observing run is you have to take some calibration images and some calibration spectra, and it was just luck. He pointed the telescope at this part of the sky when he took his calibration images. It's amazing, really. And we had to do that because you can't really apply to an observatory and say, I found a weird thing, can I take a picture of it? That's not really how it's supposed to work. But the spectra we got was remarkable. It told us two things. It told us that the Volva was at the same distance as this galaxy. So that tells you it's big, it's galaxy-sized. It also told us that the Volva was made of hot gas at about 50,000 Kelvin, but that there weren't any bright stars in it. So now the question is, how have I heated a dwarf galaxy's worth of hot gas, 50,000 Kelvin, without stars? So we didn't know. We came up with some ideas. And the idea was that maybe we'll blame the galaxy that's next to it. Sometimes when you feed material onto a black hole at the center of a galaxy, you can get jets that shoot out. Rob Fender, my boss, is giving a talk to QS about this end of this term, start of next term.
That's the one.
The last one this term, yeah. And please be nice to him. Like, it'd be, just if he's happier, my life is better. Yeah, I'm going to tell him you're a great audience. That would be fab. Anyway, he'll tell you all about jets from black holes. And in spiral galaxies, they're rare, but they tend to be at right angles to the disk. So, okay, so if this black hole is active, there could be a jet here, and it could be exciting this gas, which is then glowing. This is a perfectly reasonable theory, and it just requires there to be lots of hot gas falling down onto the black hole at the center of the galaxy. Well, that's okay. We can check that using an X-ray telescope, which we did, and we saw absolutely nothing. There's no hot gas at all at the center of this galaxy. And so the idea, which we've worked on for years, and I'm increasingly convinced is right, is that we've caught this galaxy as it's changing. The distance from here to here is about 50,000 light years. So the Volva is experiencing the center of the galaxy as it was 50,000 years ago. So it takes time for jets or energy or information to propagate. So there's nothing there now, but if 50,000 years ago we'd looked at this galaxy, we would have seen a bright core with lots of hot gas falling down onto it. In fact, this galaxy would have been the nearest quasar, the nearest very active galaxy to us. But the black hole has shut down just in the time it's taken for light to get from here to here. So this one object tells us that galaxy-sized the black holes of the size that we find at the center of galaxies, they can switch quickly from being active to being quiet. We found lots more of these because other volunteers on the Galaxy Zoo project wanted to be like honey, and they wanted to find their own Volverpen. We actually found a whole load of Volverpies, which is the diminutive, smaller versions, but each time we can use them to say something about what the black hole was doing tens of thousands of years ago. About a third of the galaxies that we've looked at show signs of having black holes that go quickly from being active to quiet. So if you read the textbooks, they'll tell you that quasars are different from galaxies because they have active black holes at their center, but actually these things switch on and off really quickly. A discovery that came from somebody who wasn't an astronomer doing the very scientific thing of saying, what's the weird thing? So a serendipitous discovery can kick off all of these scientific exploits and adventures. And there are lots more examples like that in Galaxy Zoo and in other projects. But I promised you I'd talk a bit. So we've talked about why this is important. I've hopefully convinced you that it's fun and interesting to chase unusual objects. Let's talk a bit about how to do this now. And let's talk about how to do this now, given that computers have got clever, which is the other change that I've talked about. I've talked a bit about telescopes becoming automated and data sets becoming very large. We have 1 million galaxies in the Sloan survey. But in the last few years, you only got to read the newspapers to realize that machine learning has become a hot topic, like computer vision and the ability of computers to recognize and interact and predict the world around them has become really quite impressive. Particularly image recognition. If I feed Google an image of King's College Chapel, it will tell me that that's in Cambridge. If I feed Google these days an image of, I don't know, Parker's Piece, it will recognize Cambridge. It will recognize the train station and all the rest of it. If you feed Facebook a picture of your friends, and you're not in the UK or Europe, where such things are banned, if you're in the US, and you feed Facebook a picture of your friends, it will identify them for you with reasonably high accuracy. Computer vision and pattern recognition, particularly via a technique called deep learning, has become very powerful. But it depends on having lots of examples. You train a modern machine learning algorithm by giving it lots of examples. If I want it to recognize galaxies, well, let's say if I want it to recognize animals, I just give it a lot of pictures of animals and say, this is a giraffe, this isn't a giraffe, this is a giraffe, this is a giraffe, this isn't a giraffe. It's a very tedious process, and you need to assemble your training set. But the quality of the machine learning depends almost entirely on the quality of the training set. This is why, for example, both there is progress being made with autonomous vehicles that can drive themselves, because it's easy to collect lots of data for what typical road conditions are like and train a car to work out how to behave in such circumstances. But it's also why that's a really difficult problem, because every day when walking down this street, you encounter something unusual that was particularly in Cambridge, right, where there's a string quartet running around the market square or whatever else. Is the man in the bin still here? So, yes, people are nodding. Good. Okay. If you don't know what I'm talking about, ask me at the end. But it's not hard to think of examples where the computer has never encountered that before, and that's bad news for a machine that's trained only on examples. And so the capabilities of modern machines slightly depend on the problem that you give it. And I've started to think of this as something called the Zorilla problem. Galaxy Zoo is one of many projects that we run in a platform called Zooniverse that asks people to participate in science projects. And one of the non-astronomy projects we run is a project called Snapshot Serengeti that has motion-sensitive cameras on the Serengeti National Park, and the task is to identify the animals. And these are all pretty straightforward. There's a giraffe, lion, porcupine, stripy horses. You basically get the idea. And for example, the giraffe, we had lots of people take part in this project because people like looking at animals on the internet. So we very quickly assembled about 250,000 images of giraffes, feed that to a neural network, it learns a giraffe. We built the world's best open source giraffe detector, which if you need it, you can download and run it. It's on GitHub, help yourself, and you can check your environment for giraffes. It's pretty reliable. That's fine. That works because we had 250,000 labeled images of giraffes. One of the animals that the biologists are interested in is the Zorilla. Is there anyone who hasn't heard me talk before that knows what a Zorilla is or had heard of a Zorilla? It's a small skunk-like thing. This is the best image that we've got of them. They appear from our camera network one time in every 3.6 million photos. So I could run this camera network for a century and I still wouldn't have enough Zorillas to be able to train a neural network to find them. And in astronomy, we have lots of Zorillas. This is not a real photo, just to be clear. This is a Photoshop thing. But my point is that in astrophysics, as I've tried to argue, we care about the unusual stuff. It's quite unusual in machine learning. If the Google image search goes wrong one time in a million, who cares? If we miss the objects in our survey that are 1 in a million, we really care, because that's a whole new scientific story that we're missing out on. So we need to be able to find these really unusual things. And I think the way to do it on the scale of modern surveys is to combine human and machine. And so that's what we've been working on. We started on this with a project called Supernova Hunters. This looks at, asks people to compare reference images of galaxies with new images with potential supernovae in. And we use a very basic algorithm to get rid of anything where there's no change. And then we have volunteers and an algorithm that's trained on expert data rank each of the remaining candidates. And what's really interesting is that these, oops, that's interesting, there we go. Hopefully you can still see that online. Type in chat or wave at me if you can't see the slides. So yeah, we're good. So each dot here is a candidate supernova. On the x-axis is the machine score. So over here are things the machine is sure are supernovae. Over here are things it's sure it's not. And then this is the volunteer score. So things at the top people are sure are real, and at the bottom thing people are sure that they're not. Green is nonsense. Red or yellow are potential supernovae. Blue are asteroids, which for now count as supernovae, right? They look like supernovae, and then you realize they're asteroids because they move, which is a later step. So the task here is to divide the green stuff from the other colors. And I like this graph because I think you can see that if you tried to do that by hand, you'd put a line somewhere like that across it. In other words, you use a diagonal line to split the other colors from as many of the green as possible. So it's not a vertical line, it's not a horizontal line. So the combination of human plus machine outperforms either one on their own. So the volunteers are doing something different from the trained network. And when you dig into it, what's happening is the volunteers are finding the really unusual stuff and the weird examples, and the machine is doing the bulk of the work more efficiently than we can do. So this is quite promising, this potential combination. We've actually found other ways of combining human-machine classification. If you go to Galaxy Zoo today, you'll find there's an enhanced workflow where you're actually given galaxies that the machine wants to know about. So we have an algorithm running in the background all the time called Zoobot that's classifying galaxies, and it knows which galaxies it thinks humans will be better at classifying. And so we feed those to volunteers, and then we have this nice productive loop that goes back around, and that turns out to be an excellent way of training one of these modern machines. We can also, this is what I've been working on most recently, try and find actual methods of deliberately searching for the unusual. But I should probably try and define unusual at this point in the talk, because we're near the end. So this is a sort of rough diagram. Don't take this too seriously. I've been trying to think about how to explore large surveys. So on the x-axis is how interesting something is. And if you want to be a bit more quantitative, let's say that's how worthy is it of following up with another telescope. So, you know, this is, I'm not even going to get out of bed for it. This is, I suppose I'll take a picture if I'm looking at it. This is, I might go to the observatory. This is a high priority target, and this is, I'm going to phone all my friends and insist that they look at it immediately. Something like that. It's slightly inspired by one of my favorite wine writers, classifies wine by when you've had a sip of it, how much of the wine would you buy from one sip to the vineyard? So I think it's kind of a very similar sort of scale. And then this is how unusual it is, which we'll talk about quantifying later. So in the bottom left of this diagram are normal things, right? These are your bread and butter galaxies, your everyday stars, your normal asteroids. In the top left, so these are things that are unusual but boring. And if these didn't exist, this would be a much more easy problem. So these are artifacts. This is my camera broke. This is the diffraction spike of a bright star. This is Elon Musk's satellites have just got in the way, although they're becoming a bit more normal. But you know, these are boring but interesting. Sorry, boring but unusual. The bottom right is kind of interesting. What's interesting but not unusual? I think, I haven't really thought about this program. I think this might be beautiful things, right? The classic spiral galaxy. An everyday comet that doesn't get particularly bright. Arguably, planets in the galaxy, now we know they're really common. So these are things that are interesting, but they're not unusual. So that's not what we're interested in. What we want is stuff that's in the top right. We've got to somehow try and find things that are both unusual and interesting. And this turns out to be a really difficult machine learning problem. I think it's a relatively unusual one. So there are a couple of approaches we tried. Well, one is to copy, you know, the internet. Because the other place, another group of people that have this problem of showing you things that are interesting and unusual are Amazon, who have an incredibly large selection of possible products to sell you. They need to find the things that are interesting to you, and they need to find, ideally, the thing that's uniquely interesting to you. So they do that by a recommendation system. Here's a completely random Amazon page, but you'll all be familiar, of course, with the fact that you're being recommended other things. And in this case, I have some sci-fi, I think. Dal McDermott, who beat me on University Challenge, so that's a bit upsetting. But First Light's very good, that's Emma Chapman's book, and Anna Rutherford's always great. So you know, Amazon knows what I am interested in because I bought stuff from it, thus it has an idea of what else I should look at. My friend Michelle Lochner has built a version, no, shut up, see, technology. Michelle Lochner has built a version of this called Astronomical that you can play with online, which gives you a selection of galaxies. You tell it which ones you're interested in, and then it tries to show you galaxies that are like the ones that you're interested in. You can imagine interacting with the whole Sloan survey like this and quickly filtering to find the galaxies that you're interested in. We're investigating whether that works in general. We can also, slightly more technically, take one of those deep learning, machine learning networks that I talked about earlier that have learned to classify galaxies, and we can sort of hack them apart and get them to put nearby galaxies that are like each other next to each other. So this is a mapping of the whole Sloan survey, and then we've zoomed in a bit. So this is a machine's attempt to put similar galaxies next to each other. And if we do that, we can then say which galaxies are furthest from the crowd in this arbitrary space. When you do that, you get quite good results. So at the top, these are the most normal galaxies in the Sloan survey, the top 3 rows. And in the bottom are the most unusual, according to our neural network. What you can see is we've actually done quite a good job here, because down at the bottom, these are all mergers like this one, or galaxies with strange disturbed forms. There's a couple of things that are a bit odd. This is just a star that's in the background. Not quite, this is a double nucleus. And these are all pretty boring galaxies. So this sort of filtering works quite well. You want to have a go yourself. My friend Kate Story-Fisher, who's a grad student in New York, has built a tool that you can export this. And the URL actually, yes, there it is on the side. So it's very easy to remember. So it's just weird galaxies with the dot before the ES. So it's a Spanish URL. So I recommend going, you can explore this space. This is the computer's idea of how you should look at galaxies. And here I've selected some unusual ones, and they turn out to be interesting artifacts. So your challenge is to find somewhere in this space which gives you unusual but interesting galaxies. I think if we could pull this off, if we could build machine tools that let us find interesting, unusual things, then we can use it for all sorts of science. We're building new surveys that will require these tools, but we can also, of course, use it for SETI. We can use it to try and find the aliens. There are big SETI programs underway. This is the Green Bank telescope in West Virginia, which, thanks to donations from, this is now slightly awkward, the Russian-Israeli oligarch, Yuri Milner, is devoting a lot of its time to a project called Breakthrough Listen, which is listening to potentially unusual radio signals that might be associated with alien life, or maybe astrophysical discoveries. They were in the news recently because they had their first decent candidate, so called BLC1, Breakthrough Listen Candidate 1, which seemed to be coming from Proxima Centauri, the nearest star to the sun, which we know has at least 1, possibly 3 planets, possibly more. And it took them about a year to dig into the data and discover that that wasn't a real signal. But if we can monitor the whole sky with radio telescopes and pay attention to things like fast radio bursts on, and pay attention to the unexpected, we've got a good chance of doing SETI. And we can do it as well with the optical. This is the Veritas array, which normally looks for showers of light associated with gamma ray bursts, but which has been used for what's called optical SETI, looking for flashes of light that might be aliens communicating with each other, and so on. In short, if you have the right survey, the right tools, and you can pay attention to the right things, there's still a chance to make discoveries. This is the Vera Rubin Observatory, or at least the building that will house it in Chile, which is now very much underway. Rubin is an amazing project. It has a telescope as big as many of the biggest telescopes in the world today, with an 8 and a bit meter mirror, but it's a survey telescope. It scans the whole sky every night. It's going to provide 30 terabytes of image data a night and about 10 million alerts a night that something has changed. Asteroids have moved, stars have flickered, and supernovae have exploded, and so on. In the first month of operation, which is expected probably right at the start of 2024 now, we will discover more supernovae than we've seen since the beginning of the telescopic era. But in that data set, there will be things that no one has dreamt of. And our challenge, I think, is to stay open to being surprised by the universe. I'm sorry for the rambling talk. I hope that was fun, and I'm happy to answer any questions you might have. Thanks a lot.
Thank you so much, Professor Chris Lintott, for the very amazing talk. Let's move on to the questions. Please raise your hands if you have questions, and for those online, put it in the chat if you have questions.
Sure. Let's start here.
Obviously, transients sort of pop out because they are very different in terms of long-term observations. So obviously, you can achieve luminosity simply by doing a longer integration. But when it comes down to resolution, which I think is critical to teaching an AI system what the structure is that it's looking at, that's going to be constrained by aperture or interferometrically by baseline. My question is, are we reaching the limits of resolution?
Yeah, I think it's important to think about both, right? Because you can extend in any direction. The new generation of extremely large telescopes will help us. So the EELT, the European version with its 39-meter mirror, with the adaptive optics. So the other thing these telescopes have that doesn't really get talked about is very advanced adaptive optics that essentially removes the effect of the atmosphere. So we're not limited by being on the ground. Will give us new, very high resolution images. The trick is going to be finding the things for them to look at. So the things like Rubin, the survey that I talked about at the end, and one of the points is to provide the target list for those big new telescopes, because what you can't do, unless you're very patient, is the whole sky at depth, at high resolution, because that needs the larger telescopes. So you have to sort of do a wide field survey at pretty crappy resolution and then follow it up. We always, with Galaxy Zoo, we get occasional emails from people saying, why are the images not better? And it's because they're used to Hubble Space Telescope images. But this is a survey. We were in a rush and we were on the ground. So you build a wide field telescope and so on. So I think the combination is needed. There is a game that some people play that I'm not sure what to think about, which is that you can take a particular form of modern machine learning called a GAN, a generative network, and you can train it to produce, you can play the game of here's a low resolution image, here's a high resolution image of the same object. You train it like this, and then it learns to predict what the high resolution image will look like. So then you can take the galaxies that you've only got a low resolution image of, and it will spit out a realistic high resolution image. Now, what the status of that is scientific, and how you use those high resolution images is difficult, because that's not a high resolution image of the galaxy. But there are ways to use that to answer some of the questions. So one can cheat slightly, but not for the unusual objects. So yeah, good. It's a really good question.
Why this telescope with the Rush with that? Why do it have jagged edges around the edge?
Oh, the Green Bank one.
Yeah.
Yeah, it does. Yeah, it's very striking when you go there. Cheapness. Basically, it's a radio telescope. So at the wavelengths they're looking at, those jagged edges don't show up in the imaging, and it's actually made of many different panels. So all the panels are roughly square. So that's all. So yeah, no, it's just you can get away with it with a radio telescope. Whereas if you did that with an optical telescope, you'd create very strange images. Okay. So yeah, that's why. Yeah. Furthest away object we've ever seen. We've seen objects whose light has been traveling towards us for about 13 billion years. So one of the games, actually, I was going to talk about this and I skipped it because I ran out of time. One of the games you could play is you could take your telescope and you can point it at one patch of sky for a very long time. And when you do that, you get an image like this. So in this image, there are only a few stars. I think there are 4. Everything else in this image is a galaxy. And these are all very, very distant galaxies. We see them as they were when the universe was very young. We've just launched this new telescope called James Webb, the James Webb Space Telescope, and it's designed to look even further back. So they're busy getting the mirrors to work and getting the instruments to work. But by the end of the year, we should be able to beat this image and we'll see even further. So it's great to ask a question where the answer will change in the next few months with any luck. But thank you for asking. Yeah.
So you said that half of all the gold in the world was created by neutron stars.
Correct.
But the immense gravity of the neutron stars makes it very hard for the gold to escape. So how has the gold escaped?
That's a good question. So I probably was speaking a bit too quickly. So it's created by neutron star collisions. So it's when two neutron stars collide together. And that's what produced that image of what I thought was NGC 4993. Was I right?
Yeah.
Yes. Excellent. Good. Points to me. So yeah. So you can see this bright dot, which actually briefly outshone the whole galaxy. So what that tells you is this is an enormous explosion. And so like a supernova, but on a grander scale, the material gets thrown out and mixed back into the next generation of stars. But that's a really, really good question. I can't see chat on here, by the way. So if there are questions online, you should.
There is one that says, on the subject of odd and interesting, will we ever see recycled electronics again?
This used to be a podcast that I did with my friend Rob Simpson. We've never stopped doing it. So whenever Rob and I are in the same place with the recorder, there'll be another episode. It just doesn't happen very much anymore. Thank you, whoever that is, for asking that. Jonathan, was I rude enough about comments? I tried to be nice, yeah.
So I'm going to follow that up. As far as I know, Sloan's survey didn't discover any comets. Was they unlucky or looking in the wrong way?
They were looking the wrong way. They did find some ashes, so the cadence was wrong. So Sloan didn't often go back to the same bit of the sky because they were trying to once image the whole sky. So they've got some serendipitous asteroids because they took 5 images of each bit of the sky. And later on, they did a supernova bit where they did keep going back, and that helped a bit. But so they were unlucky. So this is actually the biggest problem with the Rubin survey at the minute, is that we're in the middle of what are called the cadence wars. So the nominal design says we will survey the whole sky every 3 nights. And it turns out no one wants to do that. So if you're an asteroid person, you want to see, or near-Earth asteroid person, you need to see a bit of the sky and then you need to come back an hour later because you're trying to find something that moves fast. If you're only a galaxies person, you probably care about the stability of the image. So all I want to do with my galaxies hat on is just take a week's worth of observation of one part of the sky before anything changes in the optical system, and then do the next bit. Cosmologists have their own idea. Comet people have their own idea. I'm involved, as you heard in the introduction, we're trying to find interstellar objects, things like Oumuamua that flew through the solar system. We need to look in different parts of the sky. So we're currently trying to balance all of these things out. But I don't think the comet community have realized yet, but Rubin will find an awful lot of comets. The magnitude limits are deep, and we think we've got a good pipeline for finding moving objects. Whether what you do with hundreds of very faint comets, I don't know, but presumably the population and the orbits will be interesting. I have to come back and talk about interstellar objects because they're fascinating. We're doing interesting things with them. But yeah, so Sloan weren't trying. Rubin, I hope, will do better. And yeah, one of the things that's going on in the solar system community is, like, I suspect if we announce the comets that Rubin finds via the standard methods, we'll swamp people. So we need a new way of announcing boring comets, in the same way that we're having to invent ways to announce boring supernovae as well, because there'll be a supernova most nights. One of the things we're going to do, I think, by the way, is that societies like QS will be able to adopt a bit of the sky, and you can have a feed of things that happen in your bit of the sky and be responsible for checking and following up interesting stuff. So Comet QS might stray through the relevant field, and have a word, and we'll get you a good bit. Maybe something in the eclectic, do you think, Jonathan, or do we want to be just up? Where would be most interesting?
I would go for either the poles or relatively close to the sun.
All right, I will have a word, but that sounds good. Anyone else?
So you talked about the funny format being possibly related to quasars turning on. how many Pfizers are there? How many Wolverts are there? And can that tell us anything about the lifetime of Pfizer?
Yeah, no, that's a good call. The trouble with that idea, we've sort of half played. I've got two unfinished papers on this topic, and the reason they keep being unfinished is that for the Wolvert to exist, we need there to have been some activity in the center, but we also need there to be gas out here to be lit up. So if you think about it, if there wasn't any gas, when you look with a radio telescope, there's cold gas here and here, which we think is the remnant of a merger. We actually think this thing has come past, disrupted this disk, thrown out a long tidal tail, and this bit of it happens to be lit up. I don't understand why there's this hole, by the way. This is one of the big things that worries me about the Wolvert. Suggestions welcome. Anyway, so the trouble is that we don't have a good handle on how many galaxies have enough cold gas around them so that if there was activity, there would be a Wolvert. What I can tell you is that of the galaxies where we've seen a Wolvert, 1/3 of them seem to have undergone this recent fading. So that tells me, I think, that if you're the kind of galaxy that does this on-off stuff, that you maybe spend 2/3 of your time on and 1/3 of your time off. And I think that's a reasonable inference from the data, but we're in the middle of a big Hubble Space Telescope program to take more images of these things and to nail down the timescales a bit more.
Do you have any more questions from the audience? Right, if not, that would be it for the talk. That was a very engaging and interesting talk we have. Thank you again to Professor Chris Lintott for the talk. Thank you everyone again for coming tonight. Just an announcement to make. We will be having our annual formal dinner on the 14th of March in the coming 2 weeks, I think, on a Monday. So every class member is invited to come. Yeah. Otherwise, that's it for tonight. Thank you so much, and hope to see you around here next week.